Welcome to Lecture Online, and our next challenge here is to find the electric field due to a line charge, but in this case we're going to have the line charge in a horizontal position instead of a vertical position, and we're trying to find the electric field at this location right there. A distance A away from the beginning of the line charge, and a distance B away from the end of the line charge being a length L. And of course what we want to do is find a small little element on this line charge, and there'll be a small amount of dq on there, and we're going to find the electric field here due to the small amount of dq. And so what we can do then is say, okay, we're going to have an electric field in this direction to the small little segment right there, and that's going to be a small amount of dE, and that's going to be equal to k times dq, and I have a dq like that, divided by the distance between them squared, and distance here would be x, so it would be x squared. So that would be the small amount of electric field at that location to the right caused by that small little segment. Now the linear charge density is lambda, and so we can say that lambda therefore is equal to the total charge placed on the segment right here divided by the length L. So that would be the linear charge density. And so we could say that the dq in this case, dq, is equal to the linear charge density times the length of the segment, which would be dx. So we could replace dq by lambda dx, which is probably what we want to do because we want to make sure that the differential matches the variable in the equation. So in this case, we're going to write this is equal to k, and instead of dq, we're going to write the linear charge density times dx divided by x squared. And so what we need to do now is we need to then sum up all the small little segments, and when we sum them all up, that will equal to the total electric field at that location. So therefore the total field, electric field E, is equal to the sum of all the little dE's, integrating from x equal A to x equal B, and so that would be equal to the integral of k lambda dx over x squared from A to B. Now k and lambda, it's not a very good looking lambda, so let me close the gap here. So k and lambda are constants, they can come out, and we can write this as dx times x to the minus 2 power. So the electric field here is equal to k times lambda times the integral of x to the minus 2 dx from A to B. Of course, that integral right there, that is equal to k lambda times that would be x to the minus 1 power divided by the new exponent minus 1 from A to B. And so that is equal to k lambda times 1 over x to the first power. Now I left off the negative sign because I'm going to switch my limits. So that leaves me with a b and an a. So it's a little trick. Whenever you end up with a negative inside here and you want to evaluate it, you can simply turn that into a positive and switch the limits around. So this is equal to k times lambda, and when we plug in the upper limit we get 1 over a, minus when we plug in the lower limit we get 1 over b. Now that makes sense because b is bigger than a. You can see b is bigger than a, and so 1 over a would be a bigger number than 1 over b, and so therefore you get a positive result, so that looks good. Now what we could do, we could put q over L for lambda, or we could just leave it as it is. And, well, this is interesting. There's no variables left in there. Okay, so that means the electric field, if we want to make it into a vector, is equal to this quantity in the positive x direction. And there you go. That's how we find the electric field due to a horizontal line segment.